So, ladies and gentlemen, let's come back to texture mapping. So we all know by now what texture mapping means and how texture mapping is performed. Now we have said that what texture mapping essentially does is we take a piece of geometry, a quadrilateral as here, or probably two triangles. We assign so-called texture coordinates to the triangle vertices. And by assigning these coordinates, we essentially determine the the region in the specified texture map that should actually be mapped onto the piece of geometry. And we have also looked at how the texture mapping process is realized. And in particular, what we need to understand here is the so-called texture interpolation stage. Now, that is a stage in the rasterization-based graphics pipeline, which on current graphics cards is supported in hardware. And what it means is just the following. And therefore, let us just look briefly at how texture mapping is performed. Now, for each fragment that is generated by the rasterizer, the rasterizer interpolates the texture coordinate or the texture coordinates which are specified at the vertices and assigns the interpolated texture coordinate to the fragment. And then in the pixel shader stage, for every fragment, then by using the interpolated texture coordinate, the texture is evaluated or looked up at that coordinate. And that is what we see here, for instance, in that illustration. Now we can think about this in the following way. Let us really assume that we would have a 2x2 texture map. Then we see here, these are the initial texture values which are stored in this 2x2 texture map. Then we have said that these so-called texels, they have locations in the local texture coordinate space. Now we could say that this texel here has the coordinate 0, 0, and this one here is at 1, 0, and the one here is at 1, 1, and the one here is at 0, 1. But now it is clear that if the rasterizer interpolates texture coordinates that are specified at the vertices, the rasterizer may generate a texture coordinate for a fragment which is, for instance, 0.6, 0.6, indicated by that circle here. And then the question is, of course, which texture value now should be assigned to that texture coordinate or to the point with the texture coordinate 0.6, 0.6. And we will see in the following that we have different options to do that. One of the options, of course, is to use interpolation between the texture values. And another option would be to just say, okay, assign the value of the texture element that is closest to that coordinate in texture space. First of all here, briefly, the shader program which does such a texture lookup. So that is the instruction which we perform here. And what we do for this, first of all, we have to specify an additional texture coordinate buffer, where for every vertex we store a texture coordinate. And then by defining an appropriate pixel input type, with, in this case here, we call it .tech, with a structure component tech, which allows us to access the per vertex texture coordinates. We can simply use the texture coordinates now in that function shaderTexture.sample, where we specify a certain sample type. We will come back to this a little later, and in particular now specify here the texture coordinate which the rasterizer has interpolated from the per vertex texture coordinates to the fragments. And by means of the interpolated texture coordinate, I can now just call the shaderTexture.sample function, which returns the texture value at exactly that location. And then I can use the texture color in whatever way I want. Okay, and you see again, no, you as a programmer, you don't really have to take care how the access of the texture using the interpolated texture coordinate is done. No? That is done by the shaded texture or by the sampler stage. No? That is the texture mapping stage, which is provided by the rasterization-based rendering pipeline. No? You just have to make sure that you specify the texture coordinates per vertex, and then just call the sampler stage in order to let this stage evaluate the texture value at that interpolated location. So now there are two different situations that occur when texture mapping, when using texture mapping. No? And these are the two situations you see here. So what do we see here? Now let's start here with the left-hand side example. So we see here the pixels, no? In the pixel raster. Now let us assume, for instance, we have a viewport which is comprised of 3 by 3 pixels. No? And we have always said, no, that a pixel is essentially an aerial element. No? So it's an element that covers a certain area, no? And that is indicated here by the red square. No? That is the size of a pixel. And you can imagine that now we are looking through that 3 by 3 pixel raster. We are looking at a quadrilateral or two triangles. No? And now we have mapped a texture onto that quadrilateral, a texture of size 5 by 5. No? So we see the texture here is a 5 by 5 texture, so comprised of 25 texels. And we see here in that situation that the size of a pixel is far less than the size of a texel. And we call this the magnification situation, where the texel size is larger than the pixel size. On the right-hand side here, we have the situation which we call minification. Here we see now that the pixel size is far larger than the size of one texel, meaning that every pixel now, so to say, covers a number of texels in the two-dimensional texture. So these are the two situations, and now we have to think about, okay, what do we want to see when either in magnification or in minification? And so far we have also always said, okay, when working on a fragment, and a fragment is always assigned to a pixel, then we say that the color of the pixel is determined by what we see through the center of that pixel. Meaning in this case here, okay, so my pen is red, I don't see it, so imagine that we have the center of that, oops, I'm sorry. Let me go back again here, okay. Okay, so on the left-hand side, now, if you would ask, okay, what do we see through the center of that red pixel here? No? So of course, we could say, let us assume that we have the texture coordinate at the surface point, which is seen through that center, pixel center point, and then we evaluate the texture just at that point. No? And now the question is, of course, we see that this red pixel here is falling somehow in between the 4 texels here. And the question is now, okay, which of the texel colors should be assigned to the surface point that is seen through that red pixel? Should it be a combination of all the 3 texel values here, or should we only assign the value of the texel here to that pixel? And that is essentially telling us immediately the 2 options we have now in that magnification situation. And if we go to the minification case, then we see that things are becoming a little more complicated, because what we see now is, okay, if we look through that pixel, then we see that essentially we see many, or the contribution of many texels to that pixel. However, if we stick to our described strategy to only evaluate what is seen through the center of that pixel, then of course we only would determine one single texture value, one single texture value that is seen when looking exactly through the center of that pixel, and this value would then be assigned to the entire pixel. And we can immediately imagine that this somehow gives us a, let's say, incorrect representation, because in fact what we see when looking through that pixel is a couple of different color values coming from all the texels that are seen through that pixel. And the question then is, okay, can we not somehow determine the colors of all these texels falling into the same pixel, and for instance just use an average of all these colors and assign it as the pixel color? And we will see that this is exactly something we will do, and we will show different options how this can be realized. In order to handle these two cases, magnification and magnification, we use what we call texture filtering. Texture filtering now tells us how to combine the texels to determine the pixel color. In minification, we have said that the pixels are larger than one texel. In magnification, we have said that the pixels are smaller than one texel. And now we can use different so-called texture filtering methods in order to handle both cases. Now, one filtering method is what we call nearest. We just choose the texel closest to the pixel center and assign the color of that texel to the pixel. Or we can perform a linear interpolation, or in 2D or 3D a bi- or trilinear texture interpolation, so to obtain a smoothly interpolated texel value and assign it to the corresponding pixel. Or we can use what we call MIP mapping. That is also a linear or an interpolation, a multidimensional interpolation, but now in a stack of textures of decreasing resolution. And this is then a way to handle the minification case, where the pixels are larger than one texel, because what we can actually encode in this stack of textures, we encode, so to say, the average colors of multiple texels, which we can then look up during rendering in order to handle that minification case. And we will look into the details of this later on. Let us first look at the magnification case. Now we have said magnification, the pixels are now smaller than one texel, and we have already seen when looking at the example here. Let me just quickly remove that. Now we have already seen that here. Now what we can do, if we look at that red pixel here, and we ask, okay, what is the color of the texture that is seen through that pixel? Now we see that somehow the surface point seen through that pixel falls between these four texels here. And now we can either do what we call nearest texture lookup or interpolation of the closest texels, and that is exactly what we see here. So the nearest neighbor texture filtering simply means that for every pixel or for every fragment that is of course assigned to a certain pixel, the rasterizer creates the interpolated texture coordinate. And now we take that interpolated texture coordinate and we ask, what is the nearest texel to that texture coordinate? And the color of that texel is then assigned as the fragment color. And it is clear what we get by this. For instance, in this example here, if the texture is a checkerboard texture comprised of only red or white texel colors or texels, then it's clear that by nearest filtering, we can never get any color in between red and white. We either get red or we get white, depending on whether the interpolated texture coordinate is closer to a red texel or a white texel. Now, and on the right-hand side now, we see what happens if we say, okay, no, we don't do a nearest filtering, but we do, in this case here, because we have a two-dimensional texture, we do what we call a bilinear filtering. That now means that we always, for every interpolated texture coordinate, we determine what are the four texels that are, so to say, surrounding that texture location, and then we bilinearly interpolate between these four texel values to obtain a smoothly interpolated color per fragment. And that is what you see here. Now we get a smooth transition between red and white, because we always interpolate between the surrounding texels, which are either white or red, so that then we get an intermediate color between white and red. Yeah, we see also how this looks on this slide here in detail, or how this process then the nearest filtering and bilinear filtering looks. So here we have again on the left hand side the nearest filtering. So we see here these are the texel values, and we see here now the location of the interpolated texture coordinate, where it comes to lie in the local texture coordinate space. And by nearest, we just say, okay, if we have that, then we determine to which of the four texels this one here is closest. That is now the texel A, and then the color at that point P is the color of that texel A. And in contrast to this, on the right-hand side here, we have what we call bilinear interpolation. And bilinear interpolation now just means the following. We can really imagine it in the following way. We create a quadrilateral, and at the corners of that quadrilateral, we assume the values of the four texels, which are, so to say, surrounding that location here. And then we just ask the question, okay, how can we now interpolate the four colors at the texels A, B, C, and D to that location P here? In order to do that, we use what we call bilinear interpolation. And the bilinear interpolation, let me just sketch this here, is just an iterative linear interpolation along the two, so to say, local coordinate axes. Let us assume we have that quadrilateral here. We have values here at the corner points. And let us assume, so we are in local coordinates here, so meaning that we range here from 0, 0 to 1, 0 to 1, 1 and to 0, 1 here. And we have a point here with a certain, let's call it, x, y coordinate. Okay, now how do we interpolate? We could just say the following. We could just say, okay, let us assume that is, so to say, the x direction, that is the y direction. So now what you could say is, let me just draw that line here at the x location, so to say, of that point here. And then we could just say the following. First of all, do a linear interpolation along this edge to obtain a value here. Do a linear interpolation along this edge to obtain a value here. And then you use these two linearly interpolated values in order to perform a third linear interpolation along this direction to obtain the value here. And that is what we call bilinear interpolation. And here you have the bilinear interpolation equation. So the x and the y are just the local coordinates of the point P in that square here. And if you just write the equation down in the very same way as I have just said it, first of all, a linear interpolation along that one, a linear interpolation along this one here, and then a final linear interpolation orthogonal to this, then you will see that this gives you exactly the bilinear interpolation equation you have here. You could have also done it in a different way. You could have said, okay, we first, let me draw this line, we first linear interpolate here to get a value here, then linear here to get a value here, and then a final linear interpolation here to get the value here. So this gives exactly the same result. Both can be executed by just evaluating the bilinear interpolation equation we have here. So the good thing is that bilinear filtering is free. So it's supported by the hardware. Of course, it takes a little bit of time, but because it's hardware supported, it can be done for billions of fragments in a very, very short time. And yes, this is, so to say, the de facto standard on current graphics accelerators when it comes to magnification in texture mapping. Yeah, let us also look at the results. No? So here, first of all, we have the nearest filtering. And you see here, no, you only see in the colors of the final fragments the initial texture colors. No? And you see in particular here, no, and here. No? So you don't get a smooth texture color interpolation. No? It's more kind of a jaggy color pattern. You have this kind of staircase, this abrupt changes here. No? You don't have a real smooth color representation. Now we see, in contrast to this, the bilinear interpolation. Now let me go forth and back. No? So nearest, bilinear, no? Nearest, bilinear. No? And now you see you get a much smoother impression, because now, in addition, so to say, to the initial color values which are stored in the texture map, you also get smooth interpolations between these colors. No? And this then manifest in the final images as seen here. So you could also now further improve the quality of the interpolation, for instance, by going to what we call cubic interpolation. So this is bilinear interpolation, and this would be cubic interpolation. So we will not go into the details of this, just to understand. Cubic interpolation simply now tries to, let's say, fit a higher polynomial through the texture values in order to get an even more smooth interpolation of the colors which are finally generated. You can also do this via a shader program, but it's not supported in hardware. No, it's not supported natively by the texture unit on the graphics card. But if you are aiming for highest quality, no, then you could also implement such a cubic interpolation filter in the fragment shader. So that's the nice thing about the programmability of current hardware. So in a fragment shader, where you can not only access the texture values at one single texture coordinate, but you could also, of course, sample the texture at multiple other coordinates. You could then just sample all the values you would need in order to fit a higher polynomial through the given set of samples, and then by this to realize an even more smooth interpolation filter.